Can we get to the 300 watt hours per kilogram? Yes, we can. That's where we said we got there at CoinCell. We believe we can get there for the pouch cell as well. We don't see that going to be an issue. Can we do better than 300? Yes, we do believe we can. It's just cell engineering. The potential limit for this tech is around 1,000 watt hours per kilogram.
Well, today I'm joined by the founder and CEO of Australian-based Graphene Manufacturing Group, Craig Nicol. And this is the third time that I'm actually speaking to Craig, and they're developing a really exciting battery technology, Graphene Aluminum-Ion batteries. They also manufacture graphene and a couple products with that graphene. But Craig, it's great to have you here talking to you again. As we open this conversation up, we've talked about this topic multiple times, so I don't want to just talk about the same thing over and over and over, but I do want you to go ahead and introduce to us your battery technology, the graphene aluminum-ion battery technology that you are developing, and what makes it different from other graphene aluminum-ion batteries that are on the market being developed right now.
Yeah, thanks, John. Look, it's good to be back on. I have to say the graphene aluminum-ion battery being developed by us has very few other proponents. So when I can talk about how it's different to other aluminum-ion batteries, but there's very few others to talk about. So it's probably best if I just to say how it's different to a lithium-ion battery, and that is, it is very different. For a start, it doesn't have any lithium. It's a big one. The aluminium-ion is being used in this to carry the ion across, and then the charge goes around, obviously, through your phone or wherever your car. And all we're taking is an aluminium ion, but it actually goes from, and this is the interesting thing, it goes from the anode to the cathode. So our ion actually goes the opposite way to a lithium-ion battery goes. So there's a few things there that kind of make it interesting. We don't use right now the aluminium ion or the atom itself. We use an aluminium chloride atom. That's one electrolyte. We actually have 3 electrolytes we've been developing, but the one that we mostly focus on is an aluminium chloride atom, and that is merely coming off the aluminium anode, and then it goes over and gets stored in the graphene. So the graphene is used not to carry the charge, but it's there to hold the charge. And that's probably something I just wanted to be clear about. So whilst it may seem like we've got a graphene battery, it's actually an aluminium-ion battery. And the graphene is used to store the ion, which then allows the electron to go around and power your phone and power the car or whatever else is going on with you when you're using the battery. So yeah, the graphene is there to store it on the cathode. Now that's completely opposite of what you're having with a lithium-ion battery. Your graphene or your carbon is typically on your anode in a lithium-ion battery, and that's because the ion goes the other way. So there's a few things we have to do differently. Now, in deeper science, there's even more interesting things that we do. But I think for now, that's the most kind of high-level difference, that it is a very different type of chemistry, but it's, as we'll discuss today, it's proving to be quite successful.
So just so I'm understanding this correctly, a lithium-ion battery, as you charge it, the ions go into the anode, which is a carbon-based, usually it's graphite. Mm-hmm. But whereas what you were saying here is when you're charging your aluminum-ion battery, the ions are actually going into the graphene, which acts as the cathode. So it's the ions are moving into the cathode versus the anode during charging. That's what you're describing?
That's right, yeah.
Okay, just making sure I got that clear for our audience as well. Okay, let's go ahead and move into the reason why we're doing this conversation. And it comes down to the fact that you recently announced the fact that you now have built 500 milliamp hour prototype pouch cells. So I want to talk about that. I want to talk a little bit about maybe your development to this point, what you've done previously, how you got to where you are today. How many of these prototypes have you made? And how are you building these? Are these hand built? Are you using automated processes? Just talk about that a little bit.
Sure. So I've got one here for you. So this is a graphene aluminum-ion battery. It's about 500 milliamp hours. You can see it's reasonably thick. There's a lot of thick material in there. It does really well on power density. It does okay on energy density. The numbers really aren't worth talking about yet because this is just an assembly to be able to show that the concept works and at scale. We've made, we're making probably 30 a week maximum. You're doing different types of material testing, your different types of material thicknesses, types of material testing, and then you're doing different types of chemistries as well. Which this gets us to is providing us an understand how multi-layer cathode and anode, that the engineering of it as well, which is very important, and then all the dimensions, how it can all be brought together into one battery. So that's very a big step for us, and it's what's called BTRL, or Battery Technology Readiness Level 4, which means we're scaling the cell. Now, previously when we were talking to, we were kind of Battery Technology Readiness Level 2 or so, or 3, and that's where you're making coin cells and then occasionally doing pouch cell. But this is now we're into pouch cell. So what we're seeing though is a very similar type of fast charging and the ability to alter the variation of the charging rates and discharging rates. As we saw in the coin cells, we're seeing that as well in this pouch cell. And we're pretty much seeing all the other type of attributes that we really enjoyed with the coin cell. So we're very happy to see it's coming across. If anything, it's improving since we were working on the coin cell. So the pouch cell is obviously the main game.
Before we actually started recording, you'd mentioned that you haven't done a lot of testing yet, but talk about what testing you have done, what testing will be done in the future, and just that topic in general on this prototype battery.
Sure. I mean, the type of things you normally see are temperature testing, humidity testing, low point, high point testing. We generally think that we will be able to do below zero. So we should be able to do below freezing point. So that for us means there's a lot of benefits there above lithium already. We should be able to see well above the 50, 60 degrees Celsius, maybe even higher than that. So that again, it means it's got a higher range. Don't think we'll see any need for cooling. We can go into that. That's a whole other podcast. There's a lot of technology in our graphene which enables the heat dissipation. So the cooling requirement is likely not need to be needed. So that's another advantage. The testing around the robustness of it, so the rate discharge and rate tolerance, that's something we've seen over and over again. Its ability to be almost, it loves being abused. Almost, being whacked with heavy charge. Typically how you wake a battery up, it tells you a lot about the battery technology. Lithium batteries, they kind of get woken up it's like waking up a teenager out of bed. You got to do it very slowly. It could be very dangerous if you don't. So when you turn them on, when you activate them, you can take up to 2 weeks to actually activate a lithium-ion battery. And there's typically different steps, and if you do it a different way, you can actually make it problematic, and the battery can fail. With our battery, we typically put the electrolyte in, seal it, and then we can activate this in a couple of hours, and then fully discharge, and then fully charge, which you cannot do also with lithium batteries. So there's a number of key differentiators there as well. Now, we haven't done destructive testing yet. Pretty sure though it's not going to be an issue there. There's a lot of reasons why we believe there will be issues. So typically you would do destructive testing with lithium-ion battery, where you put a nail into it, and you might have seen someone's lithium-ion battery testing nail tests, and it's pretty interesting. Normally it catches on fire and it has a big explosive kind of reaction. We haven't done that yet, but pretty sure that that's not going to be an issue, because the reactivity, there is no reaction there. There is no the ability for it to catch fire. So in terms of the number of different tests we've got to do. We will do those as we progress through to the final stages of our cell. And once that cell is at that point, we'll do even more data testing, and then we'll be able to release that data testing as well.
I wanted to circle back to something you mentioned, waking up the battery cell, and I assume you're talking about the formation process there versus a lithium-ion battery. I'll look up the exact number and I'll put it up on the screen, but this is something that I highlighted previously about Tesla. They had developed a technology that made the formation process more efficient, and they were talking about how much of the cost of setting up a factory and making a battery, how much of that was related to the formation process. So if you're able to drastically shrink down the amount of time it takes to get the battery ready to actually be used, it's extremely significant when it comes down to manufacturing. So you covered that. It's not a question. I just want to highlight just how important that is, and not
it's really
pass by that
because
quickly.
Every battery in the world is activated, is formed and tested and recorded. Every one.
And it's expensive.
It's very expensive. And if it takes 2 weeks, which is most lithium batteries, everyone's got to be stored and then tested for those 2 weeks.
Okay. I know you mentioned you didn't want to really talk about energy density, but I have to bring this topic up. I think it's really important. I think it's something that we just need to briefly talk about. I know you haven't tried to optimize your test cell, your prototype test their cell for energy density, but I believe you're only using one of the ions from aluminum. So we'll talk about that in a second.
Yeah.
Do you think that cell's closer to what you had in 2021 with 150 to 160 watt hours per kilogram? And how realistic is your claim on some documents of 290 watt hours per kilogram? Basically, I guess the question here is, where do you think you kind of are roughly now, just a rough estimate now? How do you get to that 290 watt hours per kilogram? And what role does the number of electrons that you utilize, what role does that play in getting to that?
Yeah, so there's a number of levers. First one is weight. The next one's just around cathode capacity. So how much our ions can store provides in effect, the energy that you can store, or the amp hours that you can store in there. So that's all about graphene optimization, and to provide that storage. It's an ongoing evolution of our cathode. So first you try to reduce the weight and the thickness and the thin, try to reduce the thickness down, and you try to optimize the ability to also take out any kind of resistance in the battery, although it's pretty low resistance battery at start, and then you try to increase the capacity. So it's a two-stage step, because capacity obviously provides a pretty big indicator, because that's the numerator. Then there's the third point, and that's the voltage, because you obviously got amps, weight, and then voltage. Now currently we're roughly 2 volt nominal, which is typically what an aluminum chloride. There's no mystery there. Aluminum chloride sits around the 2 volts. Now we've done two things there. One is we're able to do some cell engineering to actually bump that up to about 3.7 volts, and inside the cell. So we've that enables us to be able to give a complete replacement for lithium. Can we get to the 300 watt hours per kilogram? Yes, we can. That's where we said we got there at CoinCell. We believe we can get there for the pouch cell as well. We don't see that going to be an issue. Can we do better than 300? Yes, we do believe we can. It's just cell engineering, and also some potential different things we can do with cell chemistry to get to, say, the 4 volts. So there are some levers that we're nowhere near pulling on, and we know they're very big levers. The potential limit for this tech is around 1,000 watt hours per kilogram. But when you put in a cell which doesn't need cooling, and can be put in potentially a plastic pack because it's not going to catch fire, like a lead acid battery, say, which uses plastic packs. You reduce the weight, so you've also got to look at the end energy density of the pack, and there's significant benefits in that we just won't have, which will definitely be in our favor as well once we start to build the packs and the modules, and then be able to offset all of the things that we've gone through, all the benefits. They'll come in and they'll start to be, oh yeah, we don't have that, so therefore their energy density for the pack is even better. So that's yet to be done as well.
That's an important benefit to your technology when you actually come to pack level energy density, not having to have as much cooling. So the end net result, the finished battery pack, even with a lower watt hour per kilogram cell, which you probably won't have when you actually do this, but even if you did, you would still be on par with typical battery technology. So that's important. I do want to step back to voltage for a minute. You mentioned, sometimes for some applications, voltage doesn't matter. I do believe for an electric vehicle, voltage would be crucial. My understanding is if you built a battery pack that had half the voltage of a lithium-ion battery, in order to hit the same capacity, you would have to have twice the number of cells. Because if you go in series, you increase the voltage. If you go a cell arrangement in parallel, you increase the capacity. But wouldn't that end up being like double? Am I understanding that incorrectly? But isn't 3.7 volts kind of needed when you get to an EV battery pack in the future?
So in summary, no, because it all washes out in the data and the energy density. So if we need 2 cells, well, our cells will take that into account with the energy density. There's really only one technology you need to have 3.5 volts, and that's Bluetooth, because Bluetooth needs 2 volts to actually work. And so you can't really you need 2 of our cells in, and then if you have 2 cells to run a Bluetooth, it just becomes difficult. You could do it, but it's not simple, not as simple as just a lithium-ion battery, which comes in and just runs Bluetooth. So personal electronics really need a 2 volt minimum. So ours is not the best for that right now. But as I said, we're already working on a 3.5, 3.7 volt battery cell, just with cell chemistry.
Excellent. Let's move to graphene for a minute. So your company is the Graphene Manufacturing Group. You manufacture graphene. We've discussed this. I don't need you to go into the process in depth, but because we've discussed that in past videos, you have a way of producing graphene that is a lot more efficient. And you also mentioned in past videos that the specific quality of graphene that you're able to create specifically for battery use, of course, is important because it has to be really dialed in. Can you talk about how much of that high quality graphene are you actually able to manufacture right now? And what are projections for the future? What does that look like for you guys?
Yeah, so I mean, we don't really talk about our capacity because it's not connected to something that we're actively selling. I mean, we make the product, the graphene, for our batteries, for our lubricants, for our concentrates, and then for our energy saving coatings, our heat transfer coatings. So those things are what we're focused on with our graphene production. We're building a graphene expansion project right now, and that should be finished by the end of the year. That's a fully signed off process, because obviously we work with hydrogen and methane, and so that needs to be done with the right safety precautions and all of the right controls. And then we obviously got to be able to produce at scale with that quality. So our existing graphene plant's still running, and we use that to be able to make the different graphenes that we need for our different products, and both production for our energy saving products, but also for the graphene for our batteries. So it's not about production for now, because it's really around getting it right for the different applications, especially for the battery. But as I said, we're finishing our expansion project, and then what we then aim to do is then complete this project to further expand it. So the first expansion project is put in all the infrastructure and then to set it up to be able to produce. Then once we've actually got the battery where we need it, we can then go and install new modular production systems. So in effect, we're waiting until the battery is exactly where we need it to be, because we're still optimizing the graphene and as we optimize the battery. So we don't want to go build a whole lot of graphene production capacity and realize actually there was this one little tweak that we should have done to be able to get the battery. So we need to float both up as our needs for our products go.
That makes a lot of sense. Your point of not massively scaling graphene production until you really nail down the battery makes a lot of sense. It doesn't make sense to build out all this infrastructure and then have to change it. So that's logical. Let's go back to the battery cell development process. So you said you're at like step 4 right now in your process. Talk about where you go from here, what comes next. When do we actually see these battery cells actually make it into a commercial product? And what is that first commercial product? And just talk about that process a little bit.
Sure. So the first thing we got to do is make thousands of these for people to go test. We have a contract with Rio Tinto, obviously the largest aluminium producer in the world, miner producer, and then one of the largest miners in the world, hands down. And they need to decarbonize all of their mining equipment, which is important, and processes, because that's where all the battery materials is coming from. So if you don't actually decarbonize all the mining of these materials that people want to put in their batteries, like the copper and the aluminium, then you're kind of defeating the purpose. You're kind of biting the hand that's trying to make it get there. So we're trying to help them get there. That's we have a joint development partnership with them. So we would see us hopefully giving them, because they've got first access rights to these batteries for their sector and more broadly. So I think they'll see these batteries providing hopefully that opportunity to decarbonize their large trucks, and also various different other applications that they've got thinking about, energy storage, as well as there's potential marine and rail. Now, how that actually goes around different sectors, I can't be sure. We've got many different sector leading companies talking to us, the kind of world leading companies, trying to understand how they can engage with this technology and bring it into theirs. And I think, that time will tell, but we've got definitely energy storage, the ability to do very rapid startup and discharge for grid. When grid fails, you want to have that rapid discharge into the grid, and which our battery can do. Then there's diesel engine replacement, which quite honestly, if that's all we did, we would never have to do anything else, because that's obviously goes into marine and rail and large trucks, and also generation power. And then there's aviation. I think we will see some of our batteries in electric vehicle takeoff. So being able to have vertical takeoff needs a really high power discharge, which our battery can do. Over time, I think you'll start to see them in vehicles, maybe premium vehicles first, but you might not see them all. So you might see lithium, and you might see a few of ours, so combinatorial type batteries. You might see ours sitting to take some power and give some power whenever it needs it. Meanwhile, it uses the lithium batteries otherwise, because every battery is going to have a role. A fundamental believer in that.
Interesting. Very, very interesting. Well, thank you, Craig. I appreciate everything that you've shared with us today. I'm excited about your progress, and definitely look forward to you guys developing the next prototypes, the larger prototypes, and going from there. But thanks for coming on, and thanks for your time.
Anytime. Thanks, John.
Do let me know what you think about all this in the comments section below. I'd love to hear from you. And also, I'd like to say once again, thank you to all of those of you who support me through Patreon. Your support makes a big difference and really does help make these videos possible. If you'd like to find out more about how you can support my work through Patreon, I will put a link in the video description. Thank you so much.